Good evening. Thanks a lot for having me. I'm Jason Hallstrom. I'm with FAU. As Fred mentioned, I direct a new research institute at FAU called ISENSE. This is the Institute for Sensing and Embedded Network Systems Engineering. I'm new to South Florida. I joined FAU in January. This is my first time interacting with the South Florida Technology Alliance. Appreciate the opportunity to address the group tonight. I'm going to try to give you a perspective on the academic community's view on where IoT began, and then I'll back up and spend a little bit of time talking about some of the applications that are happening in IoT right here in your own backyard at FAU. So I want to preface this overview talk with a comment, and that comment is that our team only plays team science. When you look at the grand challenge problems that face society in the US and face society overseas, these are not small problems. We're looking at how do we manage natural resources that are decreasing, how do we manage our finite energy reserves, how do we manage growing traffic problems, how do we manage the mega cities that are burgeoning across the world where we have tens of millions of people living on very small pieces of land. Those problems are not going to be solved by individual scientists working in their laboratories or working in isolation in their offices. These are problems that require large interdisciplinary teams that bring to bear diverse disciplinary perspectives and bridge academics with folks from industry to tackle these problems head on. So I have the privilege of presenting some projects that we're engaged in at FAU, but these projects are driven by large teams of collaborators. So we only do team science at FAU. That's what this talk's going to be about. So I want to start and just give you a sense of when academics talk about IoT, what is the picture that they have in their mind? I think that the picture that's up on the screen now, that's what academics think of when they think IoT, and it's a simple picture. So the idea with IoT is that you have some devices that have sensing capability, you have devices that have actuation capability, they're connected to a gateway. That gateway has a connection to the internet, and on the other side you have client applications. Those client applications could be collecting information from the sensors, they could be making decisions, they could be informing decisions through visualizations and presentation tools, or they could be actuating the environment, and that's IoT in a nutshell from the academic perspective. Now, the academic community is aware that there's a lot of buzz around IoT. So we've heard about IoT in trade magazines as a first-class entity for about 3 years. Just within the last 12 months, IoT has started to appear in academic journals and in academic conferences as a first-class construct, as a first-class concept that requires study by itself, its own first-class kind of thing. But we have this sneaking feeling that we've seen this before. So I'd like to do a little bit of stepping back in time by about 6 decades. Back to 1952. Back in 1952, we saw, or we eventually saw, what was at the time the largest distributed sensor networking installation. It was done in '52. It was something called Project SOSUS that was done by the Navy. Project SOSUS was initiated because of fears that Soviets had ballistic capabilities on their subs which could reach our shores. And the fear was that the Soviets would be taking advantage of German technology that came out of World War II. So SOSUS was a sound observing system. That's what SOSUS stands for. And the first deployment consisted of 40 hydrophones. These hydrophones collect very low frequency acoustic information, and they were first deployed not too far from here off of Eleuthera, which is in the Bahamas, along a 1,000-mile stretch, 240 fathoms of water. At that time, in '52, there was the capability to do real-time identification and real-time tracking of submarines. Project SOSUS at the time was not highly publicized, but it eventually grew to scale around the entire coastline of the United States, and it remained in operation until the early 1990s when it was ultimately turned over for monitoring marine mammals. But that's kind of the birth of IoT from the academic perspective. Now let's move forward by 2 decades to 1972. In 1972, NASA launched its NavSat-1. And shortly after the launch of the NavSat-1 satellite, USGS, right here in Miami, partnered up with NASA to deploy the first wireless telemetry platform to monitor water levels in the Everglades. So when folks wonder where did IoT start, it turns out IoT started right here, not too far away. The way that real time worked in 1972 was like this. The telemetry platform collected information about the attached sensor. That information was transmitted to the NavSat-1. The information was relayed from the NavSat-1 to the Goddard Space Center in Maryland, where it was then teletyped back to Miami, where it was then teletyped to the satellite offices. So real time meant you got 3 observations an hour, and it took about 2 hours from the point of observation to the point of, from the point of sample to the point of observation. But still, you can see the start of something interesting emerging way, way back. In the early 1980s, DARPA came on board. And DARPA put their muscle and they put their money behind distributed sensor networking. And they started to look at what distributed sensor networking might be all about and what kind of operational capability that it could provide to the military. The most important outcome of this DSN initiative from DARPA, the Distributed Sensor Networking Initiative, was the development of a real-time testbed that was deployed through MIT's Lincoln Lab to do real-time tracking of low-flying aircraft using a combination of distributed acoustic sensors and TV cameras. So the technology wasn't quite there to realize what we see as IoT today, but again, you're starting to see something interesting take shape. There is no internet, so it wasn't quite there yet. It wasn't quite there. So at that time, the internet wasn't full scale. We had ARPANET. And so ARPANET, the predecessor of the internet, was used in part on this project, but it wasn't full scale. All right. Now we enter the late 90s and things are getting exciting. Technology has advanced. We've seen significant improvements in semiconductor technology and radio communication, and DARPA gets interested again. And they make a major investment through a program called Sense IT, which was Sensor Information Technology, and they began to look at this picture of what would it look like if we had access to real-time streaming information from all sorts of things. And they invested a lot of money figuring out, developing algorithms to make sense of the data that could be collected through large-scale distributed sensor networking systems. And then came the biggie, Project NEST, Network Embedded Sensor Technology. By the time NEST came around, this was in 1998, the technology stack that was necessary to realize IoT from the hardware perspective, not the software perspective, it was already in place. We had low-power radios, we had the internet, we had low-power micros, low-power flash. We had the basic building blocks, but they hadn't been assembled into end-to-end solutions, and that's what NEST was about, and boom goes the dynamite. When NEST hit the universities, it had a profound impact both in academia and in industry, and it came in 3 major waves. The first wave was in the development of new hardware platforms that enabled low power, low cost, in situ sensing at scales that no one had imagined. Well, once you have all of these platforms, all these wireless sensing devices, which were shrinking and shrinking and shrinking so quickly, you needed some good software tools, and that's wave 2. Wave 2 is the development of these software tools that allowed you to program these devices and to deploy them at very large scales and to do it sort of reasonably easily. Okay? Where reasonably easily means, as Fred suggested, that not so long ago it took a team of about 10 PhDs and 20 grad students to connect a pen to the internet. So it was getting better, but we weren't there yet. But it enabled a host of cool applications that caught the attention of academics, that caught the attention of industry. The applications that were demonstrated in the early millennium ranged from the detection of invasive animal species like the cane toad in Australia using distributed acoustic sampling, to the monitoring of civil infrastructure to detect cracks, to detect irregular sway, to the early detection of biological and radiological threats, to the monitoring of traffic to the monitoring of healthcare, and the list goes on and on and on. And so when academics think about IoT, they immediately think of wireless sensor networking, and this is what wireless sensor networking means to the academic community. So now we have this catalytic ecosystem. We have components that are being miniaturized. We have devices that are very low power and enable low power communication. We have costs that are falling. We have capabilities that are rising. And in parallel, outside of the sensor networking community, we have this vast improvement in our ability to connect machines in one part of the world to machines in the other part of the world because our communication infrastructure has improved so much. And then there was this little thing called cloud computing. And then there were advancements in data analytics. And then darn industry got in the way of this beautiful theory, and they said, we need more data, and if you give us that data, we have new markets we can open, and there are new business cases we can advance. So now you have all these exciting ingredients swirling around, and you have this pressure from industry. Something awesome's got to happen. And the something awesome that happened is called the Internet of Things. So that's the short history on where the IoT began from an academic perspective. And now I want to kind of step back and talk about what are the activities that are happening at FAU in the IoT space, not a year from now, not 2 years, not 10 years from now, but are happening right now today at FAU with our partners in the community. So I want to start just by giving you a very brief overview of President Kelly's strategic plan for the race to excellence. FAU's strategic plan was approved by our Board of Trustees in early 2015, and it's a very focused vision. FAU's growth over the next 10 years is going to be driven by investments in 4 research areas. Only 4. These are referred to as research pillars. Pillar number 1 is healthy aging. Pillar number 2 is neuroscience. Pillar number 3 is ocean and environmental science and engineering. And most exciting for us, pillar number 4 is sensing and smart systems. I don't think that there is another academic institution in the country that has recognized IoT as being central to their long-term success, long-term growth. It's a very exciting time to be at FAU. It's a very exciting time to be a part of the Boca Raton community. So it's exciting. South Florida's got a lot of cool stuff going on. When the strategic plan developed these research pillars and the sensing and smart systems pillar was developed, ISENSE was formed to coordinate university-wide activities in the sensing and smart systems area. I have the honor and the privilege of directing ISENSE, and we have only 2 missions. Mission number 1 is to serve as an engineering and science clearinghouse for sensing, communication, and data management technologies. Mission number 2 is to serve as an interdisciplinary research hub that bridges disciplinary boundaries, brings people together from different areas of the institution, and creates bridges between academics at FAU and our partners in industry in the area and beyond. That's what ISENSE is all about, those 2 things. ISENSE is organized into 3 programmatic areas. We have a programmatic thrust in infrastructure systems, what I think most people in the room here would refer to as smart cities technologies. Program area 2 is in marine and environment. This relies, again, on our regional resources. FAU has property that spans more than 100 acres of coastline. We are home to one of the world's, the world-famous Harbor Branch Oceanographic Institute, one of the premier oceanographic institutes in the world. We have a routine presence in the Everglades. This is a natural place for us to invest in sensing and smart systems. The final thrust takes advantage of our growing College of Medicine, takes advantage of the growing research capacity in our College of Medicine, and takes advantage, in a positive way, of our regional resources in terms of an aging demographic. There are huge opportunities in all three areas. These three programmatic areas are supported by an engineering R&D core, and in turn, the engineering R&D core is driven by application opportunities. So we're not counting how many angels fit on the head of a pin. We're trying to solve the problems that enable you to reach the markets that you want to reach. That's what we're trying to do at FAU. That's what ISENSE is all about. So I'm going to spend a little bit of time now talking about some applications that we're engaged in, some applications that are real. I have this cartoon up which has a picture, if you can't read it, of a guy walking with his phone, and he's walking with his buddy, and he's saying, hey, you're going to love this app. It shows me what's right in front of me. And I think it's a cute cartoon, but I think it captures what IoT is all about. Sensing at large scales is about making things that are right in front of us, but invisible to us, visible. Things that are too small to see, and patterns that are too large for us to see. So I think it's apt. Okay, so the first project I'm going to talk about is a stormwater infrastructure monitoring project. This project is deployed today in Aiken, South Carolina, and I think it has a kind of interesting story behind it. Aiken is a historic city in South Carolina, and it grew organically over time. And like lots of cities that grew that way without a predefined development plan, the hard space grew. So the buildings grew, the pavement grew, the driveways grew, the sidewalks grew, and it disconnected the hard space from the green space. And the reason that that's important, it sounds like nonsense, but the reason that it's important is that when you get just a little bit of rain in a historic city like that, all that rain is collected through a single stormwater system, and it all flushes out at once. In the case of Aiken, South Carolina, all that water flushes out into historic Hitchcock Woods, which is the largest urban forest in the country. Now, I've talked to the citizens of Aiken a number of times, and they remember being children in the city at that time of town, and they remember fondly of playing in Hitchcock Woods and sort of jumping back and forth across the little stream that ran through the woods that was formed by the stormwater runoff. Today, that stream is shown up in the picture. It's become a canyon. It's 70 feet deep, it's 30 foot wide, and it's flushing sediment down into the wetlands. It's destroying the ecosystem, and it's reducing the water quality that ultimately flushes down into the Savannah River, which is used for drinking, used for recreation, all kinds of things. So it's a very forward-thinking group of city managers. They wanted to become one of the highlight cities for green infrastructure redevelopment. How can we treat our stormwater in a way that is aesthetically pleasing and relies on natural green practices? So they were interested in doing curb cuts, bioswales, cisterns, rain gardens, things that the citizens could enjoy in the parkways, but which would also treat stormwater, but there's a catch. And the catch is, it better work, because it's going to cost a lot of money to do even a small number of these. So we partnered with the city to do a pre and a post assessment through an IoT solution that monitored the amount of rainfall coming down, monitored the amount of rainfall that was captured in the soil using arrays of volumetric water content sensors. They measure the amount of water contained within a sphere surrounding the probe. And then we installed acoustic Doppler current profilers, which measure the amount, the rate, the temperature, the conductivity of water contained within the actual sewer system. So this is great. This gives us the ability to do what's referred to as a full water balance. If you know how much water comes beforehand, how much water comes down, how much water flushes out, and how much is stored in the soil, you do the BMPs, the best management practices for stormwater, and then you look, what was the change, what was the cost, was it worth it? So that's the IoT solution we built for the city. You can't see it very well, but this is a Google Maps view of the city of Aiken. If you zoom in a little bit, you see another view that you can't see. And you'll have to take my word for it. There are a lot of little dots on that picture, and each one of those little dots represents an acoustic Doppler unit installed within the trunk line of the sewer system. We worked with the city to get those installed, and that's what it looked like. So you're opening up manholes, you're sending lots of students down there, because the faculty aren't going down there. So you do what you have to do. And then we developed custom hardware to connect to those acoustic Doppler units. and we used one of these unlicensed radio bands to communicate to a wireless mesh networking solution that we built, which covered the whole of the city. So that's what the solution looked like. Well, then we built some tools on top of that to provide city managers with real-time information on that water as it fell, as it was trapped in the soil, and as it flushed out of the waterway. And we provided, of course, cloud management services to store the data, and we did some analysis for them to show what was the return on this investment. So there are lots of interesting outcomes from this project, but one of the ones that I really like is that even if you've never looked at flow through a stormwater system, if you look at the graphs for flows through Aiken, South Carolina, you can tell right away that something's not right. Because if you have an uncorrelated flow in one location, so a flow where you routinely see water flushing through the system, but there are no correlated flows elsewhere in the system, you got to take a pretty careful look at what might be happening. Do you have a dry cleaner nearby? So there are lots of interesting things that come out of this. Okay, project number 2, motivated by a simple observation. Today in the United States, we're going to consume 408 billion, with a B, gallons of water. So how much water is that? So we'll put it in perspective. That's 1,430 gallons of water for every person in the US. That's 8 billion bathtubs filled with water. It's enough water to fill the Empire State Building 1,470 times every single day. Now, there's this other problem, and that problem is that today we've got 318 million people. By 2051, we're going to have 400 million people in the US. Those 400 million people are going to share 8.3% of the available land. So we've got this real tension that's occurring between the supply of usable water and the demand for that water, and that tension is getting tighter and tighter and tighter. Well, I'm talking to business tonight, and so the solution is obvious. Water is just a resource. Water is a resource like any other resource, and if the resource is scarce, it has to be managed. And if you want to manage a scarce resource, you have to have data about the resource so that you can allocate it effectively, so that you can price it effectively, and you can place it effectively. The right amount of water, the right quality of water at the right place at the right cost. Well, it turns out that the infrastructure necessary to do that isn't in place. So we received an award from the National Science Foundation to build an instrument that could support this goal. We call this instrument an environmental macroscope. This funny terminology is meant to evoke in your mind the picture of an instrument, a single instrument, that has a broad lens that lets you take in key hydrological and environmental parameters at a river basin scale, and then to zoom in on any part to understand what's happening within the waterway so that you can allocate appropriately. This isn't pie in the sky. We've deployed this system. It's been operational for 3 years. It's deployed from the headwaters up in North Carolina all the way down to the estuary of the Atlantic Ocean. It's in operation today. It's managed from FAU's campus. We have partnerships with Clemson University and with Coastal Carolina University who help us maintain some of this instrumentation. But that's in place today, and it's been reporting and providing useful information, and we've learned an awful lot about how the water in the basin works and about how the technology for this type of solution can be constructed and can be deployed. The heart of this system, and this was just by chance for my friends from Tellit, but there's an ad for Tellit here. Tellit has lived at the heart of our technology stack for more than 8 years. We've worked with a large number of machine-to-machine modules. We have relied on Tellit for a long time because we think they're the best modules in terms of performance, and we know they're the best in terms of usability, so we've used them a long time. Around this Tellit module, we developed a custom hardware solution that attaches to water quality instrumentation. We partnered with mechanical engineers who helped us build buoys that could hold our electronics, hold our aquatic instrumentation, and all of the electronics are submerged beneath the surface of the water, and from above the surface of the water, it just looks like a normal marker buoy. And it's buoyancy balanced so that during a high flow event on the Savannah, where you can have at 3 orders of magnitude change in flow overnight, when they let out water from a reservoir, you have heavy rains. When it pendulums, all the trees and debris float overhead, and then it pops back up to the top. For the geeks out there, and I think there are a fair number of them, this is really interesting in terms of networking, because you have some very serious cellular connectivity problems when you have things penduluming to the bottom of the riverbed. But you have depth information, so you can do all kinds of interesting things about being proactive in terms of powering up and powering down your radio. So it's pretty neat. You'll see on the bottom left-hand side of that slide some folks climbing very high up on towers which were deployed out in the savannah. In most cases, our units report directly over cellular, or they report over satellite. When you don't have cellular or satellite, we set up a mesh networking solution to do hop to hop to hop to cellular. That's one of our hop points right there. For all these dangerous applications, again, we only use students from outside FAU, so it's totally fine. Okay, so again, we built some applications to support our water management agencies. We have a very strong partnership with the Army Corps of Engineers and the EPA. The tools, I'm not going to go through them in detail. I think the one point I would like to make is that the most important lesson that we learned in this application, which spans 312 river miles and requires calibration of instrumentation every 30 days, is that it's not enough to collect just observation data. You have to know how your tools are performing. So we collect very detailed diagnostics about our sensing instruments, about our wireless telemetry platforms, about our battery systems, about the mesh network, about our cloud, about our user base, and we report all that in real time in the same way that we report our sensor information. And that has been fundamental in enabling us to operate over 312 river miles with university teams. So we can allocate our resource, our research personnel and our field technicians, to where they're most needed only when they're needed, and that's because of the diagnostics. That work also is supported through the National Science Foundation at FAU. I'm extremely excited about IoT. If you peel up the covers on any one of the applications that I've talked about, or any of the applications Fred talked about, or any other application you hear about in IoT, they look the same under the covers. So what you have for all these solutions is some sensing elements. You have some connectivity solution, some physical connectivity solution or wireless connectivity solution. You have a middleware solution that typically lives in the cloud. You have analytics, and you have visualization. Lots of the tools in that ecosystem have come a very long way in a short number of years, and now you can piece these together to go after all kinds of exciting opportunities. And for us at FAU, because of our partnership with Tellit, the most challenging component of that middle portion of the stack has gotten a lot easier. We worked on developing our middleware solution for about 7 years. We had 11 Ph.D.s working on it, all senior scientists. We had about 11 Ph.D. students working on it. I'm proud of what we built. I think we built something that's very powerful, but we've worked with DeviceWise and liked it enough that we've replaced in many of our projects that center component with the DeviceWise stack. As a representative example, about 2 weeks ago, or maybe a little longer than that, 3-4 weeks ago, Jack and Decu at Tellit put us in contact with a group called Nerds Without Borders. Nerds Without Borders developed an egg, and it's an egg that has an accelerometer and a thermal sensor in it, and it's placed within a sea turtle nest. And by looking at changes in movement and changes in temperature, the folks at Nerds Without Borders have developed an algorithm to predict with quite high accuracy when that nest will hatch. So we called the folks over there, and we said, you know, we'd like to try as a test case to take your telemetry platform and to integrate it with DeviceWise. This is our first time using it. And it took us about 3 days to do that and to bring it up online in a way that's usable in the cloud, both by us and by our friends at Nerds Without Borders. We're developing a custom vision-based solution to detect the presence of litter on campus and to classify that litter. Is it recyclable? Is it not recyclable? Is it fast food trash? Is it a cigarette butt? A, because that's going to give us a picture of what litter and recycling looks like on campus, and then we can feed that information back to students through kiosks, smartphones, personal devices to try to change behavior in the positive direction. But it also gives us the ability to infer patterns of wellness on campus by looking, for example, at the number of fast food wrappers that appear near the food court, or by looking at the number of cigarette butts that don't appear as the campus becomes tobacco-free. Lots and lots and lots of other applications, and the reason that IoT is so exciting to us at FAU, and the reason I hope it's so exciting to folks here tonight, is because there's no end to the applications. This is just the tip of the iceberg, what we're seeing now, and the opportunities are unbounded. So with that, whoops, well, I lost my last slide, but with that, I want to thank you very much for the opportunity to address you tonight. I really appreciate it, and go Owls.